Hello, and welcome back to the course on quantum mechanics. So we are now on the fourth chapter for this course, which is entitled Quantum Mechanics in Three Dimensions. So we will be converting all of the lessons or all of the topics that we have discussed earlier into three dimensions. So before we proceed with the first lesson for this chapter, let us first review some of the concepts that we have discussed so far. So we have discussed about the Schrodinger equation, but in one dimension. This is given by this equation, where our wave function here is a function of position and time. And this wave function, which is just one-dimensional, is written as a linear combination of time-independent wave functions. So for the first lesson in this chapter, we will try to formulate or expand the Schrodinger equation in three dimensions. So the Schrodinger equation in three dimensions will just look similar to the Schrodinger in one dimension, but your wave function now is instead of having two dimensions, position and time, it will now have four dimensions, three dimensions in position and one dimension in time. And your second order partial differentiation operator in three dimensions becomes the Laplacian operator, so del squared. And of course, your potential energy operator here will now be as a function of three dimensions. So in general, the time-dependent wave function is now a function of the position vector, which has three dimensions, say xyz in Cartesian, or s phi z in cylindrical, or r theta phi in spherical. And it's just the same, a linear combination of the time-independent or the stationary states. So our time-independent Schrodinger equation will then become like this. So this is just the Hamiltonian acting on the time-independent wave function or the stationary wave function, equal to E and psi. So I will just explain the three subscripts N, L, and M here later. So since the atom has a spherical symmetry, we are forced to use spherical coordinates here. So we use the spherical coordinate version for the Laplacian, and we use separation of variables. So we separate psi here, our time-independent wave function, which is a function of r, the position vector r, and in spherical coordinates, this is r, theta, and phi, as a function of r, theta, and phi. And we separate it into the radial part and the angular part. So the angular part is composed of the angle theta and the angle phi. So the solution to the radial part, I will no longer be deriving this because it will take a lot of time. The solution of this are Bessel and Newman functions, and the solution of the angular part are spherical harmonics. So in spherical harmonics, there are Legendre functions involved here. So I will leave the solutions to this to you. So in three dimensions now, the probability that a particle's position r is between r and r plus dr, and its theta position is between theta and theta plus d phi, and so on, is now generalized to this. So absolute value of psi squared if your particle is in a specific stationary state psi. And so this, again, psi squared is the probability density, probability per unit measure. In three dimensions, the measure is volume. So therefore, this term here is the differential volume, dV. So dV in three dimensions is r squared sine theta d theta d phi dr. So in three dimensions, the normalization condition will now look like this. So you will now have three Kronecker delta functions: delta nn prime, delta ll prime, delta mm prime. So the value of this, since this is the normalization condition, is either 1 or 0. So let's now explain what's the meaning of the subscripts, the three subscripts n, l, and m. So you actually have discussed this before in your basic chemistry. So n is what we call the principal quantum number. Usually it's associated with energy. L is what we call the azimuthal quantum number, which is usually associated with the physical quantity called orbital angular momentum. And m is the magnetic quantum number, which is further associated with angular momentum. So in general, there are actually two types of angular momentum: orbital angular momentum and spin angular momentum. So when we will be discussing later about angular momentum, we will include spin angular momentum, where its quantum number, associated quantum number, is s. So in this case, for every value of n, there are also n values of L, and the values of L starts from 0 to n minus 1. So for instance, if L is equal to 2, then there are if n is equal to 2, then there are two values of L, 0 and 1. And for every L, m, the magnetic quantum number, ranges from negative L to positive L in integer steps. This means that there are 2L plus 1 values of m. So therefore, if you want to formulate the ground state is actually the lowest number of n is equal to 1. And when n is equal to 1, there's only one value of L. L is equal to 0. And when L is equal to 0, there's only one value of m. That is, m is equal to 0. So in this case, our ground state usually is psi 1, 0, 0. So if you now plot the time-dependent wave function, absolute value of psi squared, again, this is probability density. And if you plot it in 3 dimensions in spherical coordinates, you get a density plot. And that density plot have different shapes depending on the value of L. If L is equal to 0, the shape of that density plot, absolute value of psi squared, is S. The S, or you usually call this the S orbital. When L is equal to 1, it's the P orbital. When L is equal to 2, D, and then F orbital. So SP, D, F orbitals, you already have encountered this in your basic chemistry. So the orbital shape, again, is just the probability density plot, or the electron cloud, or the probability density cloud. So you are assured that in this cloud, there is an electron in that cloud. So the probability density depends on the density. So the denser the cloud, the higher the probability of the electron in that part of the cloud. So in general, the energy of the electron, or the atom in general, or the system in general, depends on the quantum number n and l. So if they have the same n and l quantum numbers, then they have the same energy. So these are just some of the first few orbitals. So when n is equal to 1, there's only one value of L, L is equal to 0, and one value of M, M is equal to 0. And that is the ground state, psi 1, 0, 0. Now, when n is equal to 2, meaning there are two values of L, L is equal to 0 and L is equal to 1. So again, for L is equal to 0, there's only one value of M, M is equal to 0. And this is actually the first excited state, psi 2, 0, 0. For L is equal to 1, there are actually three values of M, from negative 1 to positive 1. So negative 1, 0, and 1. And this corresponds to the P orbital. So by the way, this is the S orbital. The S orbital is spherical. So this corresponds, the three values of M corresponds to the three dimensions of the P orbital, Px, Py, and Pz. And these three states actually have the same energy. They belong to the same energy level since they have the same value of N and the same value of L, 2 and 1. So these are what we call the second excited states. There are actually three states, three second excited states. In this case, psi 2, 1, 0, psi 2, 1, 1, and psi 2, 1, negative 1. So the bar here implies negative 1. So if you go to n is equal to 3, there are now three values of L, 0, 1, and 2. So you now get the d orbital. These are the shapes of the d orbital. And for n is equal to 4, you get the f orbital. And for n is equal to 5, you're again reduced to up to only the d orbital. And then for n is equal to 6, you're already reduced up to the p orbital, and so on. So these are the different shapes of the orbitals. So usually the s orbital looks kind of spherical, and the p orbitals looks like this. So this is a probability density plot. So you can call this a probability density cloud or an electron cloud. There is an electron inside. You are assured that there is an electron inside this cloud. So there's a 100% chance that you will find an electron inside this cloud. But as to where exactly is the electron, then the probability of that depends on the density. So as an example of the wave function in 3 dimensions, we will be having this most or the simplest atom, the hydrogen atom, where its nucleus is only composed of a proton with charge plus E, and it only has one electron, negative E. So in this case, the potential energy of the system or of the electron or of this atom is just Coulomb by virtue of Coulomb's law, K, Q1, Q2 over the distance, R. So in this case, Q1 is positive E, Q2 is negative E, so you have negative E squared over R. So using this potential energy, we substitute that to our three-dimensional Schrodinger equation or Hamiltonian and then Schrodinger equation. And if we try to solve just the radial part of the Schrodinger equation using this potential energy, we can actually get the energy levels of the hydrogen atom. So the energy levels, in this case, this is only true for hydrogen, only depends on the quantum number n, the principal quantum number. It doesn't depend on L. It's independent of L. So 1 over n squared, and the term in the square bracket here is actually are all constant. M is the mass of the electron, E is the charge of the electron, h bar is the Planck's constant, epsilon naught is the permittivity of free space. So this term here in the constant, the negative value here, it's actually approximately negative 13.6 electron volt. And this is what we call the Bohr formula. So if we can actually write this, if we write some of the terms here in terms of A, the Bohr radius, so we can also write the Bohr formula similar to this, where A now is the Bohr radius. This is a constant. So this term here in the square bracket, this is actually your E1. This is the value of the energy when n is equal to 1. So that's actually E1. And that is the ground state of hydrogen, E1. It's actually negative 13.6 electron volt. And take note, this is also the binding energy of the electron to the hydrogen nucleus. It's negative 13.6 electron volts. Recall that we have discussed before about realistic potentials, that their values are actually negative. And the potential actually approaches to 0 as R approaches infinity. So at infinity, at far distances, the energy actually will approach to 0. So the energy levels, the lowest energy level is E1, negative 13.6. Then you will have, it will go less and less negative as you go into higher energy levels until you reach 0, where it's no longer bound. And when the energy of the particle is now above 0, then it becomes a free particle or the electron becomes free. It's now in the conduction band. It's now a conduction electron or a free electron essentially. Okay. So for hydrogen, so for instance, these are the energy levels of hydrogen. E1 is the ground state, E2 is the first excited state, and E3 is the second excited state. So electrons can actually, electrons in the excited state can actually spontaneously go down to the energy level. We usually call that relaxation or de-excitation. So when a particle is excited, there will come a time that it will be de-excited or it will relax. So similar with us humans, when we get excited, there will be a time that we will be de-excited. We will go back to our previous energy level. So electrons do that all the time. So that's actually what we call de-excitation. And when that happens, when an electron de-excites from a higher energy level to a lower energy level, it will actually emit an electromagnetic wave. It will actually emit light with wavelength, say, lambda. So this is the phenomenon called spontaneous emission because this happens spontaneously. On the other hand, the reverse is if an electron absorbs a photon or light, then that's the time that it will be excited. So this is emission, this is absorption. When an electron absorbs light or a photon, it will be excited. When an electron goes down or de-excites, it will emit a photon. Now, just focusing on the emission, the energy of this emitted photon or light or electromagnetic wave is just the difference of these two energy levels here. So using the Bohr formula, we get this difference. Now, take note that since this is energy of a photon, this is actually equal to hc over lambda, where lambda is the wavelength of the emitted wave. And using that relationship, we can now solve for the wavelength of the emitted wave. So by the way, Ni here is the initial energy level, and F is the final energy level. So it is assumed here that since this is a spontaneous emission, Ni is greater than Nf. So this formula is usually called Rydberg formula, where R here is the Rydberg constant. Its unit is inverse, 1/meter. Okay. So for hydrogen, transitions towards the ground state are also called Lyman transitions because they form a Lyman series. So for example, if an electron transitions from energy level 3 to 1, or from 2 to 1, or from 4 to 1, the important thing here is the final state is n is equal to 1, transition towards the ground state. So the final Nf here, the final energy level is the ground state, Nf is equal to 1. They will form actually a Lyman series. So the wavelength will form a Lyman series. And those wavelengths actually fall under the category of ultraviolet light. So on the other hand, transition to the first excited state, or n is equal to 2, that is the first excited state. Say from 3 to 2, or from 4 to 2, or from 5 to 2, they will actually emit visible light. And those wavelengths, when you collect them, they form a series called Balmer series. That's why these transitions are also called Balmer transitions. And transition to the second excited state will actually emit infrared radiation. And these wavelengths, this group of wavelengths, if you collect them all, they form a Paschen series. That's why they're also called Paschen transitions. So infrared. So let's now have an example. So first example. So the ground state of hydrogen is given as this. I will If you are interested how this is obtained, then consult our textbook. So this is the ground state of hydrogen. You will notice that it's only a function of R. It's independent of the angular components, theta and phi. So what is the most probable value of R? So what is the most probable value of R? So if your electron is in the ground state of hydrogen, so the electron is a wave. It will actually be waving. It's not like a planetary motion in which the electron just revolves around the nucleus. It's actually not like, it's actually quite complicated. So there are times where the electron is actually closer to the nucleus, and there are times where the electron is actually farther from the nucleus. But if you try to measure the position of the electron, what is the most probable value of R that you will get? So if you measure repeatedly. Okay. So I'm just gonna copy the ground state of hydrogen. Psi 100, it's equal to 1 over square root of pi a cubed e to the negative r over a. And I will just use my board mode. Okay, so this is the ground state of hydrogen, and we are asked to find the most probable value of R, the distance of the electron to the nucleus, or to the proton. Okay, so we need to maximize the probability here. So take note, the probability in this case is just psi 100 squared and then the differential volume. So in general, the differential volume in spherical coordinates is r squared sine theta d theta d phi. But since our psi here only depends on r, then we can just use 4 pi r squared dr, where the 4 pi is you can think of it as a total integral of the phi and the angular components, or the theta and the phi components, the angular components. Okay, so you will notice that if you let this term here as your, say, some probability density function P of R, then this is just P of R dr. So the problem is actually mathematical. We need to maximize P. If we want to maximize P, then it just goes to show that we need to maximize P of R. So by maximizing P of R, we are maximizing the probability P. So how do you maximize a function? So this is just mathematical. So there are tests in mathematics to determine the maxima and the minima, or in general the extrema. So you have the first derivative test and the second derivative test. The first derivative test will actually give you the extrema, and the second derivative test will determine if that extrema is a minima or a maxima. But for our case, the first derivative test will suffice. It will just give us the maximum, because the probability is always a positive value. Okay. So we need to maximize P of R. So we take the first derivative test. So we get the derivative of this with respect to R, of course, and then equate it to 0. So the derivative with respect to R of absolute value of psi squared. So square of that. So you have 1 over pi a cubed. And then square of this, you have e to the negative 2r over a. And then multiplied by 4 pi r squared. Then you equate that to 0. So I'm just going to leave this differentiation to you. This is actually a very easy differentiation. So you have, this is a derivative of product, r squared and e to the negative 2r over a. So derivative of product, derivative of f times g is f G prime plus GF prime, or F derivative of G plus G derivative of F. You do that, you equate it to 0, you equate the result to 0, and you will find that R is equal to A, the Bohr radius. So this is actually another definition of the Bohr radius. This is actually the most probable position of the electron when the electron is in the ground state. So that is the definition of the Bohr radius. The highest probability, the position of the electron in the ground state with the highest probability. So let's now go to another example. So for this example, so we will apply our previous lessons here about taking the expectation value. So find the expectation value of R. So when you say expectation value, it's just a quantum mechanical definition of average. So the quantum average, essentially. So the average of R, what's the average value of R and R squared for an electron in the ground state of hydrogen? So express your answers in terms of the Bohr radius. So this is again the ground state of hydrogen. So psi 100 is equal to 1 over square root of pi a cubed e to the negative r over a. I'm just gonna go again to my board mode. Okay. So if we want to take the expectation value of R, then we need to sandwich our position operator R with our wave function psi 100 conjugate R psi 100 differential volume. Okay. So basically, the conjugate of this doesn't have any imaginary part or complex part. It's all real. So the conjugate of this is just itself. So multiplied by this. So it's just psi squared, the square of that. So square of this, you will get 1 over pi a cubed. Integral of square of e to the negative r over a is e to the negative 2r over a. So this is a volume integral. So you have r, and then dv here, our volume integral, or sorry, volume differential volume is r squared sine theta d theta d phi dr. So this integral is actually a triple integral. So you will have 1 over pi a cubed. So let's group the r parts. You have r squared, so you have r cubed e to the negative 2r over a dr. So r is from 0 to infinity. And then for the theta integral, you will have sine theta d theta from 0 to pi. And again, for the phi part, 0 to 2 pi. So actually, these two terms here will just give you 4 pi. So the differential volume can actually just be replaced by 4 pi r squared dr. So 4 pi. So you look up for an integral formula for this, and you will get 3 factorial over 2 over a to the 4th. So simplifying and writing everything in terms of the Bohr radius, you will actually get the average R as 3/2 A. So the average position is not the same as the most probable position, okay? So this is the average positions. It's 3/2 the Bohr radius. 1.5 times the Bohr radius. That's the average position. R is equal to A is the most probable position. But those two concepts are different. You do the same for R squared, and you will get the average R squared, or the expectation of R squared. Expectation value of R squared is 3A squared. So I will leave this to you. So let's now go to another example. So this is a classic problem in quantum mechanics. You are given a particle and for a system, and you are given the initial wave function. So a hydrogen atom starts out in this state. So it's actually a linear combination of these two states, psi 2 1 1 and psi 2 1 negative 1. So the initial wave function is given as a linear combination of two stationary states, and it's also given in terms of spherical coordinates r, theta, and phi. So the question is classic question in quantum mechanics. Given an initial wave function, what is the wave function at any time t? And a further question, what is the expectation value of energy, of potential energy? So what's the average energy of this system? Oh, sorry. Okay. I'm just gonna go into my board mode here. So for this first problem, given the initial wave function, we are asked to find the wave function at any time t. So usually, we determine the linear combination coefficients. The wave function, the time-dependent wave function, is actually just a linear combination of the time-independent wave function. So in this case, the wave function at time is equal to 0. Then the initial wave function is just a linear combination of the time-independent states without the energy part or the time component part. And our wave function is actually now written in terms of this. So you will have 1 over square root of 2, and then you have psi 2 1 1 and psi 2 1 negative 1. So meaning, so since this is now written as 1 over square root of 2, psi 2 1 1 plus psi 2 1 negative 1. So meaning we already, it's now obvious. The linear combination coefficients are actually now obvious. It's 1 over square root of 2. So C1 is 1 over square root of 2, and C2 is also 1 over square root of 2. So and C1 and C2 are both 1 over square root of 2. Which means that the energy, so in this case, since the two states belong to n is equal to 2 and L is equal to 1, so they have the same energy. The energy actually is just E2. So that is basically E1. This is the ground state energy over 2 squared or 4. So this is actually negative h bar squared over 8 ma squared. So this is the energy level. Okay. So we can now write our wave function at any time t. So it's just a linear combination of these two. So you will have 1 over square root of 2 psi 2 1 1 e to the negative I e to t over h bar plus 1 over square root of 2 psi 2 1 negative 1. We have the same energy e2 t over h bar. So factor out the common terms, 1 over square root of 2 and e to the negative I e2 t over h bar. 1 over square root of 2. You have psi 2 1 1 plus psi 2 1 negative 1. So this is actually just the initial wave function, and we're actually given the spherical coordinate form of this one. So using that value, we can now write actually our wave function at any time t as negative I over 4a squared square root of 2 pi a r e to the negative r over 2a sine theta sine phi e to the negative I e to t over h bar. So this is our wave function at any time t. So you will notice that at time is equal to 0, that is the given initial wave function. Okay, so that is for the first problem. Now for the second problem, we are asked to find the expectation value of the potential energy. Now, if you want to find the expectation value of the potential energy, then you sandwich your potential energy operator between our state. So, integral of psi conjugate u and psi, differential volume. So, since in this case, our potential energy operator is just a multiplication operator, then we can combine psi star and psi to get absolute value of psi squared u dv. Now, we already know our psi here as a function of r and t. This is it. So we take the conjugate of this, multiply it by itself to get the absolute value of psi squared. So what is the absolute value of psi squared in this case? So we will actually get 1 over 32 pi a to the 5th r squared e to the negative r over a sine squared theta sine squared phi. So the time component will actually cancel each other out, because conjugate of this is e to the positive I. You multiply it with e to the negative I, so you get e to the 0 or 1. So this is your psi squared. You substitute this here, and you use the operator form of u. The operator form of u is actually negative e squared over 4 pi epsilon naught r, the potential energy of the hydrogen atom. You use this u, you use this psi squared, and our dv again is r squared sine theta d theta d phi dr. So this is our differential volume. So you substitute psi squared, this psi squared here, this u here, and this dv here, and separate it to three integrals: integral over dr, integral over d theta, and integral over d phi. So you do that, and I will leave that to you. And you make a substitution that the Bohr radius A is actually equal to 4 pi epsilon naught h bar squared over me squared. So you use the Bohr radius identity, and in doing so, you will get the expectation value of u, or the average potential energy, as 1/2 negative h bar squared over 2ma squared, where again this term here is our E1. So 1/2 the ground state energy. So 1/2 the ground state energy. In terms of, if we substitute the approximate value of the ground state, which is negative 13.6 electron volt, this is approximately negative 6.8 electron volt. So this is the average potential energy of the given system. So the method that we used here is similar to the previous chapters when we find the expectation values, but our measure now is volume, dV, differential volume. So since we are using spherical coordinates due to spherical symmetry of the atom, then dV is r squared sine theta d theta d phi dr. So for our last example, we'll have an example on the spectrum of hydrogen. So what is the wavelength range for Lyman transitions in hydrogen? So Lyman transitions are transitions towards the ground state. So Lyman transitions mean that that the final state, or the final n, is actually 1, while the initial n can be 2, 3, 4, up to infinity. So from higher energy levels towards the ground states. So we need to find the range. So actually we already know the wavelength range. we already know in which part of the spectrum are the Lyman transitions, actually in the UV range, but we need to verify that. Okay, from the Rydberg formula, lambda is actually 1 over R, 1 over NF minus 1 over NI, inverse. Now, since the final value of N is always 1, so this is just equal to 1, and we can now determine actually the range. So, if these are your energy levels, sorry, you can see it. If this is E1, this is E2, and so on. So the lowest energy transition is actually from E2 to E1. And the highest energy level transition is from infinity to E1. So this will give you the lowest energy and the highest wavelength. Take note, energy of an electromagnetic wave is inversely proportional to wavelength. The lowest energy will actually give you the highest wavelength. So for the upper range of the wavelength, that actually happens from a transition of, from an initial transition of Ni is equal to 2. And in that case, the lambda upper range is actually 1 over R, and then 1 minus 1 half or 1 half. So 1 over 2R. So 1 over 2. 1 minus 1 half is 1 half. So 1 over 2R. And since R is just a constant, this will give you, 1 half, and you take the inverse, you get 2, sorry. So this should be 2. So 2 over R. And you will get a value of 182 nanometers. So this is the upper range of the wavelength. For the lower range, that actually happens from an initial state or level of infinity. So when this is infinity, when Ni is infinity, 1 over infinity is 0, so you get 1 over R. So lambda lower range is just 1 over R. So this is approximately 91.2 nanometers. So this is the lower range. So the whole range now is from 91.2 nanometers to 182 nanometers. This is the Lyman transition range. So take note, if you will recall, the electromagnetic spectrum, the visible light or the visible electromagnetic waves are only from 400 to 700 nanometers. Below the visible range, we call that ultraviolet, and above the visible highest visible range or visible wavelength, above 700 nanometers, you call that infrared. So here, you actually have violet here, you actually have red here. So below violet, you get ultraviolet, above red, you get infrared. So in this case, 91.2 to 182 nanometers is below 400 nanometers. That's actually the UV range, where the Lyman transitions can be found. Okay. So that's actually the end for the first lesson of this course. So we are just now starting the topic on quantum mechanics in 3 dimensions. So for the next lesson, the succeeding lessons will all be will all be talking about the angular momentum. The 2 types of angular momentum, orbital angular momentum and spin angular momentum. So I will see you again in the next lessons.